This is going to be a short video where we look at benzylic and allylic oxidation. So we learned about bromination. If you have a benzyl group and you brominate it, and the reagent of choice is NBS, it will very selectively go after the benzyl carbon, and you'll get a very nice clean reaction. Allylic bromination is very similar. If you cut down again, try a mole of NBS, you'll get allylic bromination. Now this, of course, has an added wrinkle, is that you get two products because you selectively go for the allylic carbon over here, which is give you the most substituents, but then you'll have two resonance forms for that allyl radical, so you'll get two bromides. Now oxidation is similar if you use a weak oxidizing agent. And the reagent that we're going to use is MnO2. This is manganese 4, which is reasonably weak. Now this won't oxidize a simple carbon. What it needs but it will oxidize an alcohol. So if we have an alcohol in the benzyl position, and we do this reaction, it'll very cleanly go to the ketone. The same way, if we have an allyl alcohol, it'll very cleanly take that to the carbonyl. Now you can say, well, what's the big deal? You know other ways of doing this reaction as well. Well, that's precisely the point. You do know other ways of doing this reaction, but they're not specific to the allyl position. So let's say we now have this diol, and we do this reaction. Look what's happened. The OH on the away from the benzyl group has not been oxidized. The one neighboring the benzyl group has been oxidized. You can do the same thing in the allylic position, the allylic system. If we had another alcohol, let's say over here, let's say we do this reaction, then again the one next to the allyl group is oxidized. The one away is not. So that's a very useful reaction. It's very specific to benzyl and allylic reactions. Now, why does this work? Well, it works for the same reason that the benzyl bromination works so well. It's a radical reaction. It involves feeding electrons into the system and having the delocalization of the benzyl group or the double bond of the allyl group helps delocalize the electron, which is necessary, the electrons which are necessary to do this reaction. Now, if you use a more powerful oxidizing agent, we go all the way and we use permanganate. The reaction is much more exciting. So if I choose permanganate off my menu and I go up here and do the magic reaction, the compound actually cleaves carbon-carbon bonds and takes the this benzyl alcohol all the way to the carboxylic acid, breaking carbon-carbon bonds. Now, I'm not even going to, Oscar isn't even programmed to do this for the allylic reaction. Because why? Because in the allylic reaction, this whole thing just gets destroyed. You break the carbon-carbon double bond, you take these to carboxylic acid, it's a real mess. And quite frankly, Oscar isn't programmed to do it because it's simply not a useful reaction. But the benzyl group, the benzyl reaction oxidation can be useful. And the unique thing about it is almost any substrate works. And so let me go through and change this. So let's get rid of the alcohols. And we do the reaction. The reaction still works. Any carbon on a benzene ring which has an entry for electrons will work. Now, what's an entry for electrons? Well, the oxidizing agent can go for a hydrogen on the carbon. So just a hydrogen on the carbon is enough, or any kind of double bond will work. So here we have a hydrogen. Let me put, say, a carbonyl over here. Oops, I want a carbonyl. So here is a carbonyl will work. Okay. Make it an oxide carbon. We got an aldehyde. If you had a if you had a regular double bond over here, that would work. What are we going to get here? Like say this is a really nasty reagent. It takes every one of those groups to the carboxylic acid. Is there any group which it can't handle? Well, if there's no hydrogen, and there's no double bond, the group will survive. So the only groups which are not susceptible to permanganate oxidation is a carbon with basically no hydrogens, no double bonds, no triple bonds, no carbonyl, nothing. So it gives it no entry into the system. So, but that's pretty rare. Any carbon on a vinyl group will get oxidized. So that's a really nasty reaction. Now you see, there was one time before where you actually saw a benzylic reaction. We didn't really talk about it, and that's the Clemson reduction. Remember the Clemson reduction? The Clemson reduction was another reaction which was very very specific to benzylic positions, and this was of course a reduction of a carbonyl, but the reduction of carbonyls only when adjacent to the phenyl ring. So if you did the Clemson reduction where there's another carbonyl, I don't know, let me just stick it out here. I'm just making things up as I go along. We stick it out over there. That carbonyl isn't touched because it's not adjacent to the phenyl ring. So the Clemson reduction is very much like those oxidations in the sense, again, this is an electron transfer reaction, and it needs passage through that phenyl ring to get to the carbonyl. And so it's another example of benzylic reactivity. So benzylic and allylic positions are susceptible to special reactivity that normal carbon atoms are not.